This is a brief introduction to functions, and we're going to start with a simple example to explain what functions are. So take the example of wins versus points in football. You get one win, and that's 3 points. Two wins is 6 points, etc. So basically, every win gets you 3 points. We're going to ignore draws for the moment to keep things simple. So that's an example of a function. And in English, we say points depends on wins. It's quite clear from the table that the points depends on the wins. But in maths, we say points is a function of wins. So from now on, is a function of simply means something depends on something else. The next thing we're going to do is we're going to call wins x and we're going to call points y. So basically we say that y is a function of x, or points is a function of wins. And we write it like this: y equals fx. So that's the notation. Y equals fx means points y is a function of wins x. We're going to represent functions in different ways throughout this topic as well. So we need to look at those now. So again, the first way is plain English. In the last example we just saw there, you could say in words, every time you get a win, you get 3 points. Now we can say the same thing in a table. We can say that for every win you get 3 points. So if you put wins along the x-axis and points along the y-axis, well, one win you go up and across, you get 3 points. Two wins up and across, you get 6 points, etc. And you see you get a straight line pattern here for wins versus points. So the function y equals 3x, or y equals fx, where fx is 3x, that gives you a straight line graph. We can also represent functions a fourth way as a mapping diagram. So again, 0 wins gives you 0 points, 1 win gives you 3 points, 2 wins give you 6 points, etc. And you can see that the arrows are important here because you get the win first, then the points. So the arrows indicate the direction there. That's called a mapping diagram, or a relation. The fifth way of saying the same thing is if you go back to the table for 1 sec, and if you look at the pattern again, 1 win 3 points, 2 wins 6 points. Let's jump ahead. 10 wins, for example, would be 30 points. So the pattern here is you multiply your wins by 3 to get your points. So in general, if you had x wins, well, your points y is 3x. So y equals 3x is the equation that represents that function. Number 6, we can also say the same thing as a set of ordered pairs, or couples as they're called. So 0 wins, 0 points, 1 win, 3 points, etc. And lastly, we can say it as a function machine. So we can think of x as the input to a machine, fx, and y is the output. So in our example, x is the number of wins. You put in 2 wins. So f of 2 is 3 2s is 6. So 2 wins gives you 6 points, for example. We call x the independent variable. So in our case, the wins is independent, but the points depends on that. So the points is the dependent variable. So y is the dependent variable, x is the independent variable. Some terminology. Take another function like x mapped onto x squared. So for example, 2 is mapped onto 2 squared is 4, 3 is mapped onto 3 squared is 9. And we can write it like this. F is a function such that, so this is pronounced such that, these two dots here, R is mapped onto R. What this part means is R is the values of x that are allowed, and the second R is the values of y that are allowed. So R is the real numbers. So this is telling us that all the real x can be any real number, and y can be any real number. And as we said, x is mapped onto x squared. Also, the x values are now called the domain. The y values that are allowed are called the codomain. And we can show that over here as well. So the domain, the x values that you're going to use, 0, 1, 2, 3, 4, etc. 0 squared is 0, 1 squared is 1. So where they land basically is called the range. So right here we have 2 squared is 4, 4 squared is 16. So all those numbers that you land at are called the range. So the domain is all the x values that are allowed. The y is all the codomain is all the y values that are allowed, right in here, and the range are the ones that you use. There are some y values that are allowed out here, but we can't get to them from the domain, so they're not in the range. For example, -2 or any minus number. There's no real number squared that will give you a minus number here. So that's why they're out there in the codomain, but they're not in the range. Some other notation you could use here, for example, if you want to get stricter on what x values you allow or what y values you allow, for example, you might only have numbers like 1 to 10. There's even different notations slightly for inclusive and exclusive. So square brackets would be inclusive, round brackets are exclusive. You could have R plus, for example, if you only want to restrict your domain or your range to plus real numbers. So if you want to formally test if something is a function or not, generally speaking, fx is a function of x if there is one and only value, if there's one and only one value of y in the codomain for each value of x in the domain. So basically, in simpler language, you can think of the domain as a question and the codomain as an answer, or x is the question, y is the answer. And basically, a function is where every question has exactly one answer, or every x value has a corresponding y value, basically, or exactly one y value. And we've had that so far. If you go back to the example of here, for example, that's a function because every x value here has exactly one y value over here. So here's 3 examples. This is a function because in your domain, all the x values are going to exactly one answer in the codomain. We don't need to show the codomain because you just know from here that every question is going to have exactly one answer. Same here. Every question so far down to here has exactly one answer, but here's a question with 2 different answers. You can't have that, so that's not a function. And likewise over here, here's a question with no answer, so that's not a function either. You can show the same thing another way, basically. So a function, basically, every question has to have exactly one answer. You can think of the x-axis as the question and the y-axis as the answer. So when you zoom in on any function, if you pick some x value and you go up and across, you can only get one answer. So for that question there, the answer is you go up and across, and there is only one answer, as we can see here. You can also show that as what's called a vertical line test. A vertical line, if you draw a vertical line anywhere through the function, if it only cuts once, that corresponds to every question having exactly one answer. So that there would be a function because if you draw the vertical line anywhere, it cuts once exactly. This is not a function over here because there's a question with 2 answers. If you ask that question and go up and across, there's an answer. But you can also go down and across, there's an answer. So that's not a function because this particular question has 2 answers. And you can see that also by the vertical line test. If you draw a vertical line and it cuts more than once or less than once, then it's not a function. Over here, there's a question with no answer at all. That's not allowed either. So there's the question, number 7 in this case. There is no answer because it doesn't cut the graph at all. You could also show it here. This is a function because every question has exactly one answer. The question is 1, the answer is 3, etc. Whereas here, if you have 0 wins, you get 0 points. But here, if you've got 0 wins, you get 3 points. I mean, which is it? It can't be both. So that's an example of not a function because there's a question there. The question is 0 with 2 answers, 0 and 3. Now, the concept of inverse functions is important. We've seen earlier, I suppose, that fx, it does a certain operation on x. For example, you can square x or you can multiply by 3. Or, for example, this function here, you can multiply x by 2 and add 3. What if you want to reverse all that? If you want to go back to where you started, that's called, and to do that, you get what's called the inverse function. It's written like this, f minus 1 of x. It's the inverse function of fx. And here's how you find what f minus 1 of a function is. You basically reverse every step. So take y equals 2x plus 3, for example. What's the inverse function of that? Well, you just, instead of having y in terms of x, you just reverse everything, try and get x in terms of y, basically. So what you do is you bring the 3 across as if you want to get x on its own here, it's 2x is y minus 3, and divide across by 2 then, and you get y minus 3 over 2. Now, one last thing is you switch the x and the y themselves at the end even because everything is reversed, including the x and the y themselves. So the domain has become the codomain and vice versa. So x and y themselves are switched. And now you get the function y equals x minus 3 over 2. Or the inverse function is x minus 3 over 2, if you want to write it like this. So basically, fx is 2x plus 3, f minus 1 of x is x minus 3 over 2. That brings you back to where you started. If we truly understand what inverse functions are, they basically reverse x and y. X is mapped onto y is mapped onto x. Everything's reversed. So the x-axis is mapped onto the y-axis and vice versa. So what you could think of it as is this diagonal here. If you folded your page along that diagonal, the x would fall onto the y and the y-axis would fall onto the x-axis. And that's another way of thinking of inverse functions. If I had a function f of x here, for example, the question is, where would that go if I folded the page over on the diagonal here? Well, that fx would go to this line here. And that's another way of getting the inverse function, f minus 1 of x, where the x and y are reversed, basically. So you take the diagonal y equals x. That's the equation for the diagonal. Every y value is equal to the x value along the diagonal. And you can use that for the inverse of any function. If I have the function, for example, fx equals 2 to the power of x, right there, that's the function. If I draw my diagonal and fold along that line, axial symmetry, fx folds onto f minus 1 of x. So there's your inverse function right there. Plotting functions. So if we're going to look at whole different families of functions, we can save time by using a calculator, and Casio calculators especially have this fx function on them, where you can type in your function and it can give you the values of points that you can use to draw the graph of that function. Okay, so if we just come down here and have a look, so that's different for different calculators, so we'll skip that for the moment, and we'll just go and look at some of the functions you can get. So we've seen previously you can have fx equals 3x, and we saw that in the example of wins versus points, and we saw also that gave you a straight line graph through 0, 0. So that type of function is called a proportional function. We saw that basically points is proportional to wins in our example. So fx equals 3x, fx equals 4x, 5x, etc. They're all what we'd call proportional graphs. Now, the next family after those proportional graphs would be the linear graphs. So the linear graphs would be also a straight line. It's just they don't necessarily go through 2. So this, for example, goes through y equals 2, and I've drawn it down here. The graph 3x plus 2. It has a slope of 3 and it goes through 2. So they always follow the format mx plus c. That's mx plus c, linear graphs. The next family after those, if you plot them, are the quadratic graphs. So they'd have an x squared on them, and they'd be set out like this. Maybe an x squared, maybe something with x and a number on its own. So they're the quadratic graphs, and they would have normally a U shape or an N shape, like this one here. The next set after that would be cubic. So cubic starts with x cubed. And so if you look at an x cubed graph, it might have 2 humps like this. Usually they have 2 humps, whereas a quadratic is only 1 hump, a U shape or an N shape. And it goes on like that up through all the powers, and we call all of those one family, really: proportional, linear, quadratic, cubic, etc. They're all types of polynomial. Poly stands for many, nomial stands for number. So you see there's many numbers lined out there going down in decreasing powers. That's a polynomial. So that's one family of functions, and they go like this. I suppose you could say no hump for a straight line, then 1 hump, then 2 hump for a cubed. And generally speaking, you increase the number of humps or turning points in the graph the higher up the powers you go. So they're the polynomials. Now, a new family is called the exponential functions, and these are, if you like, the other way around. I mean, we looked at x squared is a polynomial. X squared, it comes from the polynomial functions. If you switch the x and the 2 around and get 2 to the power of x instead, now you've got a different type of function altogether. That's called an exponential function. And if you try and plot some values, when x is 0, get the y value, 2 to the power of 0 is 1. When x is 1, etc. When x is 2, you get all these values here. And before long, you spot that this is just doubling. The y value is doubling each time. So 2 to the power of x is called the doubling function, if you like. And there's the graph. So it's a different type of graph. It's kind of going up more steeply all the time the further you go. The number b here is called the base number, and the x in the power is called the exponent. And sometimes there's a number in front as well. Now we're going to compare some other graphs. So we can look at doubling versus trebling, for example. So doubling is 2 to the power of x, trebling is 3 to the power of x. And if we draw those graphs, 2 to the power of x is the red graph here. Trebling is 3 to the power of x, which is right there. And it turns out there's a very interesting graph in between. Obviously, first of all, trebling is steeper, as you'd expect. It goes up steeper than doubling, the purple graph here. But there's one in between that's very interesting. There's a number in maths, E, 2.718. It goes on forever, basically. So we call it E for short. It's a special number in maths. There's lots of reasons why it's a special number. It's kind of like pi is a special number. It turns up in nature all the time. It's built into maths, this number E. And so it's obviously it's 2.7 something, so it's obviously between doubling and trebling. So as you'd expect, the graph of e to the power of x is somewhere between the 2 to the power of and the 3 and the trebling graph. And there it is right there. We're going to use it a lot from now on, so it gets a special name, e to the power of x. So they're all part of the exponential family, doubling, trebling, e. But if they mention the exponential function in an exam question, for example, they're talking about this one, e to the power of x, even though they all belong to that family. You'll find that things that grow in nature very often follow this kind of a curve, exponential. Alternatively, things that decay follow e to the power of minus x. If you stick in a minus power, the graph actually goes down this way for something that's decaying. Then there's log functions. Just think of logs as the reverse of powers, or the reverse of the exponential functions. In other words, they're inverse functions of the exponential functions. So to show that as an example, go back to 2 to the power of x again, the doubling function. When x is 1, 2 to the power of 1 is 2, 2 to the power of 2 is 4, etc. So what are logs then? So I always think L for a log, L for a little number. So the little number is the log. So go backwards. The little number of 2 is 1. The little number of 4 is 2. The little number of 8 is 3. And that's the way we say it. So the log of 8 is 3. The log of 4 is 2. So it's reversing everything, basically. So if you take your points here on this graph, 1, 2, 2, 4, 3, 8, etc., well, the little number of 8 is 3. The little number of 4 is 2. So the points are the x and the y are reversed again. And that's what a log is, just reversing the x and the y values. And that's, as I said, that's the base number. So it's based on 2 here, for example. So when you go backwards, just say the base there. That's called the base. So the log to the base 2 of 2 is 1 in that example right there. And from what we talked about previously with inverse functions, that means you can now draw the graph of log once you have the graph of 2 to the power of x, or the exponential graph, because they're inverse functions. So there's 2 to the power of x right there. There's your diagonal again, and there's your inverse graph, which is log. Some useful transformations of functions. If you plot the function y equals x squared, you get this blue graph right here, y equals x squared. If you put a 3 in there inside the bracket and go through the whole routine of working out values and points for the new graph, you'll find that you'll get another graph over here, which is x plus 3 squared. You'll notice that all you have to do, there's a shortcut now. To get x plus 3 squared, all you've got to do is take your x squared graph and move it back 3 places. The same here, if you had x minus 3, and if you had x minus 3, it moves it forward 3 places. So these are all shortcuts that you can use when you're sketching functions, basically, and you're not too concerned about having it exactly accurate. You just want to kind of find out roughly where the function is. Here's another one. If you add a plus number here, for example, it shifts the graph up. So x squared plus 3, you take your x squared graph right there. X squared plus 3 is just the same graph, moved up 3 places. So x squared plus 4 would move it up 4 places, etc. x squared minus 3 would move it down 3 places. If you multiply in front of the x squared, you'd get 3x squared, so it would kind of make it narrower. So this is 3x squared in red, this is x squared in blue. So 4x squared would be even narrower again, it would be inside that. 5x squared would be even tighter. If you put a minus in front of your x squared or your graph, what that does, it reflects the graph in the x-axis, so an x squared becomes a minus x squared. So you see it's a mirror image of the original graph, basically. So they're all called transformations. By the way, there's nothing special about x squared. The same thing would work for any function. For example, if you had y equals sine x, and you wanted to find sine of x plus 3, well, all you have to do is move the graph back 3 places on the x-axis. So one last useful feature we're going to discuss is this. When you're talking about quadratics, there's this procedure called completing the square, which can be very useful for drawing graphs. So take this one, for example, x squared plus 6x plus 10. If you write that out here, and we're going to rearrange it slightly. We're going to take this number here, 6 in front of the x, get half of that number, which is 3. So over here, half the coefficient of x, which is 3, and square it, and you get 9. And we put the 9 down there. So half that number squared goes here, basically. Now, that 9, you must add on a 1 to compensate, because we still have to have 10 overall right here. So 9 plus 1 is 10. So far the whole equation hasn't changed. All we've done is change 10 to 9 plus 1. Now, why would you want to do that? It becomes obvious in the next step. It turns out these are now what's called the perfect square, these 3 together. If you work out the bracket x plus 3 squared, you end up with this. So working backwards, it's always the same. The root of x squared gives you x, the root of 9 gives you 3. And the sign of the number in the middle, if that's plus, that's going to be plus as well. If that was a minus, that would be a minus. That's the way it works out always. So we've rewritten this in a bracket. These 3 terms together is now in a bracket. Plus 1. And now if we use this and our knowledge of transformations from the previous section we just discussed, we'll remember that a plus 3 with the x inside the bracket, it moves it back 3 places. So you take your x squared graph, move it back 3 places. That's what that does. We just saw that a while ago. And the plus 1 moves it up 1 place. So that 3 moves it back 3 places. That plus 1 moves it up 1 place. And we can now sketch the graph right here. So that's what completing the square does. It gives you a nice way of drawing your graph using the number inside the bracket here and the number here that's on its own, which lifts the graph up. And that's the end of the introduction to functions.